Hello everybody, Chloe here, and what I'm going to be doing in this video is trying my best to go through an explanation of the boilerplate code that you will see when going through Rust contracts on the Near blockchain. So if you're a developer that's not used to Rust or not used to Near in general, some of this will be new to you, but the boilerplate code is just code that is going to appear in every Rust contract on Near that you see for the most part. So to do that, there is this article that goes through a voting contract. So as you go through this article, you get some background information. The background information isn't that important specifically to the boilerplate code, but it will give you more of an idea of why this contract specifically is important and some more context around the contract that's being talked about in this article. The first really, thing that you'll notice is that, the file system on Rust contracts might be different than what you're used to in whatever programming language you've come from, or if you've never programmed before, then this is the file system. So there's a link here to the GitHub page for this document. And so you have SRC, which is where the Rust library will be, which will be the actual contract. And then you will have cargo.toml. Your cargo.toml file is here. And as you could see, your cargo.toml file, which you will see if you're used to Rust, but it has specifies dependencies and other project flags. So including optimizations to improve size and performance of code, so no debugging, panic aborts, overflow checks, and forces panic on lower upper bounds. So you could see here in this code, so this article does outline all of the code. So if you go over to the GitHub page, you will be able to go through all the code there as well. And obviously you can clone this to your own repo and have it on VS Code or whatever IDE you use. But you could also just follow through the article, and the article will go through what each piece of the boilerplate code is used, or what it's for, going through introductions about it. So the first part of boilerplate isn't actually in the Rust library or the Rust contract. It is the cargo.toml file. Then when you get to the actual contract, remember it's an src/lib.rs. You can click this and get the full contract. It's kind of hard to look at this as you're reading the article, so I would suggest either pulling open your GitHub page, going to src lib.rs, and you can have this open alongside you while you go through the article. I'm not going to do that in this video, but it does help to have the full context as you're reading through each line. But this article will go through line by line what you need to know. So let's go through it. In general, keep in mind that we are operating in the resource-constrained environment of the Near protocol runtime. For any single contract method invocation, all storage and compute operations must fit comfortably within a single block time of around 1 second, along with any other calls made on other contracts. It is useful to keep this in mind as we design contracts which operate as good and performant citizens of the network. So there's an article here about thinking in gas. So if you're not used to blockchain development, something new to you might be gas. And the idea that you need to be conscious of how much gas you're using in your transactions. You want to be very, very performant. And what you might not be used to is block times. So if you get an operation done and it takes too long to go through, you have only about a second and a bit to go through all the operations in the function. So also surprising for some new to contract development, the concepts of randomness and time are not available on the same terms as is running on bare metal. So for randomness, you can't just use like any kind of random number. You need to use blockchain specific data to try and derive that random number. And for time, you don't really have a global time outside of epoch time. Or what epoch you're in. And so randomness is especially tricky, and the only real authority on time in this context is the blockchain. So any notion of time is tied directly to epochs. And what that really means is that time could be sped up or slowed down, arguably by validators who are able to increase block times or slow down block times, which is a little complicated. But if you'd like more information on that, you can definitely find information on that in the Rust docs. Oh, sorry, the Near docs. So, you know, you have the Rust SDK, Near SDK/RS, also exposes EMV random seed. So it allows you to generate a random seed from the Near SDK. But you can get into that more as you go through the SDK. So line 1, all that information about developing on Rust and going through Rust, and we haven't even gotten to line 1 yet. So as we get to line 1, you'll see that it's explaining that Near SDK, also for Rust, also provides support for writing performant contracts, including a custom binary serialization and deserialization format called Borscht. So the first time I've ever seen Borscht was using Near, and so for me it was something new and very interesting. But if you want more information on Borscht, you can click this link here. It goes to the Borscht website. You can read more. But that's for storing contract state efficiently on chain to reduce both storage and gas costs. As I said above, as the article stated, it's a performant environment where you want to be as performant as possible. If every single transaction has a cost to it for both storage and for gas, you want to ensure that you and your users are paying as little as possible for functions that they're calling. So the Borscht helps with that. So the first line of the contract brings these into scope. So if we go over to here, we'll see the first line, use Near SDK Borscht self, Borscht deserialize, Borscht serialize. Very simple. I mean, simple enough, line 1. Line 2, reading on. Clients of the contract may require a JSON format for argument and return types. Since JSON is limited to JavaScript number support, so 10 to the power of 53 is the highest number you can have in JavaScript, you need to wrap Rust U64 and U128 with some helper functions that return these numbers as JSON strings. So that's right here. And basically, all you're doing is you're ensuring that a JavaScript front end is able to read these numbers off of the contract. So you're wrapping it basically in a wrapper for these numbers to ensure that even if the number is larger than 10 to the power of 53, you are still able to read them safely. So you'll notice that the Rust native types use a lowercase u, and the wrapped types use an uppercase U. So if you see types with an uppercase U, they are wrapped. If you see them with a lowercase u, they are in Rust. So here is that line here. Use Near SDK, JSON types, U128 and U64. And so in the contract, you also see that right here on line 2. As we go through now, getting a little quicker, we're understanding where to find this stuff. You go to the GitHub, or you go to the contract, src/lib.rs, you can find all this code right there. Line 3, Near SDK RS exposes the virtual machine execution through ENV, which developers can use to interrogate the Near runtime for information like the signer of the current transaction, the state of the contract, and more. Near bindgen will be explained where used lower in the document, and account ID, balance, and epoch height all do what you'd expect them to do, but on the blockchain you have accounts. Account ID lets you search information about those accounts, like for example balance lets you search the balance of an account, and epoch height allows you to know what is the current epoch height that you're in. So all pretty self-explanatory. As well, you can get more details specifically about account ID here, and you can go through all the different Near SDK different options you can get through that. In line 4, when choosing to organize how data is stored by your contract, it is important to first decide whether you want to use key value storage or singleton storage. So in Rust, you have the option of choosing between both. In assembly script, you are stuck with using, for now, only key value storage. So down here is the actual line, use std, collections, and a hash map. So the choice of using a hash map here hints at a singleton storage strategy, And you can see the differences between key value storage and singleton storage here. So key value storage is a key value structure which is ideal for managing large contract state or cases with sparse access to contract data. So you only need to access a few pieces of data on occasion. This state is only deserialized and when accessed and otherwise remains untouched. So if you read a lot of data and when you read, you only read a small bit of it, this will be more performant. The contract will access storage directly using the storage interface and or choose a more appropriate abstraction from among the list of available collections. For singleton storage, it is a serialized representation of the contract struct. Using this type of state storage is more efficient when contract data is small and known to never risk growing unprecedentedly large. So if you know your contract state is going to stay small, then you can go for singleton storage. Or when the read operations on the data, when the read operations on the data are frequent. So if you know there's going to be lots and lots of read operations on this data, you might want to use singleton storage. Since this state is deserialized in its entirety, that's why you want it to be small, because instead of only one function or one function being deserialized, the entire state is being deserialized in its entirety every time a contract method is called. It is important to keep it small. So as we continue, so this is the point I was making about how in assembly script it does not support singleton storage yet, but I am sure that will be coming eventually to the assembly script possibilities. So lines 6 and 7, so we skip a line here, we go to these two lines, and what does that mean? Global allocator, we alloc. Okay, it's a bit confusing when I first read, actually it's still a bit confusing to me, but this is true boilerplate code where understanding it isn't as important as knowing, that it's there, what it does, and that you need it in your contract. So Rust allows us to define our own custom memory allocation mechanism to make memory management as efficient as possible. WeAlloc, the WASM-enabled Elfin allocator, has good performance when compared to WASM. In contrast, WeAlloc, the WASM-enabled Elfin allocator, would be a poor choice for a scenario where allocation is a performant bottleneck. It's small, less than a kilobyte, but does not have as good performance as the standard allocator. Okay, so honestly, it's boilerplate code, as it says here, and you include them in your contracts without much thought. If the choice of the allocator changes in the future, these articles will change and you'll be using a new allocator for now. Hopefully stuff like this is kind of just gets added into, over time, but for now, you add those two lines and you are good to go for your memory allocation. In line 9, we go through what we mentioned earlier with the wrapped types for U64. So here we have wrap types that allow contracts. So the contract is returning JSON compatible formats for big numbers. So it's doing it as a string instead of doing it as an integer. So these types are required when contract methods return large numbers to a JavaScript execution context like the browser. So the browser is a great example, which will be using JavaScript, probably not Rust. And so when you send those numbers through, they need to be wrapped so that they can be read from the browser and understood. In the following case, right, so wrapped something is of type lowercase u64, so it's a Rust type, but we want to make sure that we can serialize and deserialize it at the contract boundary when communicating with the outside world. So the contract, and then you're communicating with the client, the browser, whatever else. You want to make sure that those numbers are able to communicate. So you wrap it using the type U64, uppercase U. It's the same type, so it's still an integer that can go up to U64. But but with conveniently automated serialization. And so pretty much, from what I understand, it's wrapped with a string so that it can be read as well. So lines 13 to 15, wrap a Rust struct in, I guess, hashtag or number sign near bindgen, and it generates a smart contract compatible with the near blockchain. So this part, it was actually really helpful for me to understand that that is it. Like, that's what you have to do. So when we go to lines 13 to 15, it's as simple as you use near bindgen and you wrap a struct in it. There you go. You got a contract on the near blockchain. I mean, that's how you get one. That's what it means. So you get one started. So every Rust contract struct must be preceded with this macro. Okay, since it exposes the execution environment to the contract, which allows it to receive method calls, send results, and generally behave like a contract within the runtime environment. So you got a struct, you had wrapped it in your bindgen, and you are good to go with starting your Rust contract. Each contract has its own Singleton Storage as part of the contract account, where the contract state will be serialized and stored on chains. We talked about Singleton Storage above, and so each contract has its own for memory. Inspecting account storage will reveal a key named state, whose value is this Singleton Storage. So the state of the contract is this Singleton Storage. The following lines define the structure which will become the Singleton representation of the contract. Only one public contract should be decorated with the near bindgen macro. Only one public struct. So this public struct that is decorated with the macro near bindgen, that is the start of your contract, and everything in underneath it or wrapped by it is your Rust contract on the near blockchain. Contracts are efficiently serialized using Borscht. We talked about that above. The binary representation described earlier in this document. So you can see how you have near bindgen, you have your Borscht deserialized, Borscht serialized. Then you have your public struct, you have your contract name, and then you have all your contract details inside. Let's continue. So lines 16 to 23, within the contract struct, we can store any valid Rust type. This contract includes an example of storing a map of custom types with the hash map, specifically mapping account IDs to some related balance. So you have an account ID mapped to a balance, and that's one of the Rust types that is being used, the hash map. It also includes an example of storing a custom type exposed by near SDKRS called balance. We talked about that above. An option type, meaning it may or may not have a value. So that's kind of interesting in Rust. You could have no value. And the epoch height for keeping track of time from within this context. So again, we talked about how in the blockchain, you can't get a true sense of like global time, but you can get a very accurate sense of blockchain time using the epochs. So for our variables here, we are showing that votes is hash map of account ID and balances. We are showing that the total voted balance so far is total voted stake would be balance. When the voting ended, so none, right? So it's an option type. None would mean the voting is still open, and then whatever value it had would be, your wrapped timestamp. And then epoch height, when the contract is touched the last time. So you touch a contract over and over again, and it'll give you the current epoch height. So if the epoch changes and you call that again, the epoch height value would change. So those are lines 16 to 23. Relatively straightforward. We pop back. There we go. Right there, super easy. You can see where it fits in context of the entire contract. So let's go through lines 26 to 30. So this bit of code is part of a larger context where we have decided to control contract initialization by decorating a specific method with the init macro. So init for initialization of state. By default, all contract methods will try to initialize contract state if not already initialized, since it's possible to call any public methods on the deployed contract, but in this case, we want to avoid that behavior. So we're using this piece of code here to avoid the default behavior of every time the contract's called, state being initialized. We want to make sure the contract's ready to be used in the way we want to use it before moving forward. So here you'll see it in a larger context with the code we just talked about. Here is that init macro being used on another function so that eventually you can see that the contract has to be initialized at some point. This is how that happens. And so that is kind of the flow of being able to have some more control over the initialization of your contract and not having it be done automatically, but being more explicit and controlling the initialization of state in your contract right here. Let's skip ahead to lines 32 to 33. So decorating an implementation section, so IMPL, with near bindgen wraps all public methods with some extra code that handles serialization, deserialization for method arguments and return types. Panics if money is attached, unless the method is decorated with payable. And it does more. So you have the public struct for voting contract, then you have the implementation for voting contract down here, and then you have the init down here, which I thought was going to be up here, but let's see what that means. I mean, I already read it, but anyways. So as you go lower from lines 34 to 43, so we have the near bindgen, we have the implementation of the same voting contract from above, and we are going to initialize it. So decorating a public method with init will add some machinery to initialize the contract by serializing and saving the return value. In this case, a struct into the contract's Singleton Storage. You can add an init decorator to any public method to mark it as something like a constructor for the contract. So your contract's going to start with a certain state. It's going to start with what you put in the init function. I think that's why init was potentially supposed to be here, so that when you call it, it checks to make sure that the contract code isn't already available. But anyways, note that there is nothing special about the new method. So this is kind of interesting stuff as we go through the code. So it's saying here, like, note there's nothing special about the new method name here. It could just as well be old and it would work fine. New is just a convention. So as you come here, you get to see, so you have a public function, new, self. This new function could be anything. They're just choosing to have it be new for near. And this implementation references the env state exists to assert that the contract Singleton Storage state has not been initialized. So here we have the assert here. So this is where I feel like you're getting the same. So you're panicking if the contract hasn't been initialized before using it. But here you are checking to see the contract has been initialized. I feel like you're getting a check in a different way. So making sure it does not already exist. We don't want to accidentally reinitialize the contract at some later time and blow away any valuable state that has been captured. The init macro expects that the method it decorates will return an instance of the struct, which is being referenced by this implementation section. The return value will be serialized on-chain into the contract's Singleton Storage. If you're new to Rust, you might not be familiar with implicit returns, a language feature likely passed down to the influence of Ruby. It allows the last line of a method to be assigned as the method return value. In Rust, we get an implicit return of the value of the last line of method if we just ignore the semicolon at the end of the last expression. So this helped me when I was reading through contracts as well, because a lot of times I didn't know what was being returned or why it was being returned. But I was like, oh, that makes sense. You get an implicit return if there's no semicolon at the end. In this case, the last line returns an instance of the voting contract. So here's voting contract. There's no semicolon at the end, so it returns this. Simple enough. Rust calls these expressions rather than implicit returns, and you could read through the Rust book to get more information on that. I keep reading the Rust book, but I get like 1 or 2 chapters in, and then I stop and poke through where I need things. But I should probably just read the whole thing in entirety at some point in time. Note that the method signature of new is returning an instance of self, but could just have been, you could have written a voting contract there, except this way when you update the contract you have less changes. But so when you're here, this could have been, so public function new voting contract. So you could have been saying, implement a new version of voting contract here, but they use self to keep things, I guess, the same across what they develop at Near. So here we're going to go through some other features of Near SDK for Rust. So above was everything you saw specifically in the, sorry about that. Above is everything you saw specifically in this specific voting contract, and everything below this is going to be other, important information to know as you're developing smart contracts on Near in Rust. So you're going to have public methods. So public methods, pub fn, public function, will be exposed as contract methods available for clients to call. So if it's public, anyone can call it on the blockchain. So this is how that would look. So now with Rust, you have, you have to make sure that with all your variables, you're making sure that you're very secure and you're not changing the state of any variable without declaring that it's supposed to be changed. So you can borrow, and self. So if a method borrows self, that is the first argument in a list is and self, where the and is a Rust modifier that basically means safely take a temporary reference to, then you can be sure that it will interact with the contract state, but not change the contract state. So you're borrowing, interacting, and not changing the state. So that's and self. Then you have borrowing with and mute self. So it's mutating some sort of variable. So similar to above, borrowing a mutatable reference means that the method will interact with the contract and contract state and will change contract state. So going a level deeper here, it may be worth noting that at this point that Near bindgen actually adds code to each method of the contract which reacts to the presence of self or mute self. So that's, if you want to know what's actually happening. The additional code tries to deserialize Singleton Storage, i.e. contract state. And recall earlier from above that Singleton state contract state is stored as a value associated with a reserved key named state. Near SDKRS will call default if state does not exist, detected by a call to the env state exists. So if state doesn't exist, it's gonna call default. Otherwise, it would call default as part of preparing to run a method. So if you're familiar with Rust macros, Near bindgen is very readable. If not, apparently the author said just sit there and stare at it for a while. Personally, that's still on my to-do list to go stare at Near bindgen for a good, long, hard time. But if that's something that interests you, definitely feel free to get to that. So arguments and return types. Methods can take arguments, which will be deserialized from JSON, and return types, which will be serialized to JSON if called from external context. Making internal method calls within a Rust context doesn't require the same serialization, deserialization overhead. Internally, we can call contracts using positional arguments via any external interface, simulation tests, Near API.js, etc. If we're doing that, we have to pass JSON objects to get deserialized into the function arguments as needed. In summary, if you call a method directly without promise or ext contract API, then there is no serialization, deserialization happening. If you call from a front end, right, using Near API.js or raw RPC or using a cross-contract API, then serialization is needed. So that's just information. I think that like it's important to remember as you develop, if you're developing like just from the back end or when you think about interacting with the front end, and how you are calling your front end to put these two technologies together, or to put your dApp together. Payable methods. So pretty important if you want to actually build a dApp on Near. If you want to attach send tokens to a contract method, add payable. Decorating a contract method with a payable macro will allow the method to accept attached native Near tokens without a panic. Other than that, it will panic. If you send Near on a function that's not supposed to have Near, it's not payable, it will panic. Simple enough. If tokens are attached to a method call without adding payable, the macro will panic for the third time. Private methods. So here's where you start trying to think about doing things securely. So instead of having every method be public, you might want to hide methods from the contract's public interface. So all you have to do is not make them public. So Rust keeps things very simple in that sense, for me, in my opinion, where if you want to keep a method private, just don't make it public and you are good to go. Then you have protected methods, which go even a step further along into securing your smart contract. So if you want to maintain restricted access to some methods, so only the contract itself can call them, those are going to be private. Okay, so you have like public functions, you have private functions, so they're not on the public API, and then you have protected methods. So you're actually limiting who can call these methods or functions. So you're limiting who can call the methods based on only the contract. So sometimes a method should be available to the contract via promise call, which requires that it is exposed on the contract, but not callable by anyone other than the contract itself. This is a common pattern in Near, which can be handcrafted with a few lines of code, but this macro, This is a common pattern in Near, which can be handcrafted with a few lines of code, but this macro makes it more readable. You have, again, more information here. If you want to dig in and learn more, please definitely do that. So this feature is pending, and it is not available in Near SDK 2.0, but Near SDK 3.0 is out, so I would assume this is also out. So to end off, a brief note on contract design. Beyond the basics of writing contracts for Near using Rust, there are a few critical design issues to be aware of as a contract author. These concerns stem from a single attribute of smart contracts. They are public interfaces that can be invoked by any valid transaction on the network. So you're creating a public API that anybody can interact with. So that can have a lot of security concerns. The implications is that we should be more defensive in our development of contracts and always assume the potential for malicious or adversarial behavior by bad actors. So if it's a public API and someone just messes around and calls a function that you didn't know would grant them more Near than they're supposed to, you could assume that whoever is calling that function is going to keep calling it until the contract is run dry. Eventually, there will be a bad actor somewhere to take to gain from that mistake. So be careful and make sure that you're understanding of that. So this defensive stance will lead to safer code and more robust contracts. So for sensitive methods which are modifying contract state, it is important to check ENV predecessor account ID. So what you're doing here is you're making sure you know the access control. You know who's called this function, and making sure that they have the proper access to call that function. So you're preventing methods being called, or you're preventing things being called by a wrong account maliciously. In general, having a setter method that does not verify the caller's authority or ownership before applying changes to contract state is an anti-pattern. So on the blockchain, not checking some sort of access control is not something that you probably want to be doing to let anybody in the entire world change the state of your contract. Usually, even if it's an open contract, you want to ensure that there is some level of access control. Usually, not all the time. All contract data is essentially public information. It is a public API and can be queried via the near RPC API at will for free. This implies that any information stored by the contract should not open the contract for exploitation by bad actors. So whenever I think about this, I think about like privacy on chain. The idea of like don't create a DApp where you're putting people's private information on chain because it's available to everyone. Don't make a DApp where you're putting like bank records on chain and stuff like that because it is available for everyone to see and read and query from. So that's pretty much an overview of the article going through the boilerplate code in Rust. I will hopefully be doing another one soon for assembly script, but I actually understand the Rust way of things on Near a little bit better. But I hope I was able to clear up some questions or concerns for some people. This article specifically, in my opinion, breaks down a lot of the parts of the boilerplate code that have been really confusing for me personally. And so reading through this article really helped me to understand, when I'm reading smart contracts in Rust, what parts should I just skip over because I understand them, they're boilerplate, they're always the same, and what parts should I really dig into to make sure I understand what's happening in the logic of the flow. So I hope this video was helpful. Thank you so much for watching, and I hope you have fun digging deep into all there is to learn to be a Near developer.